drive for electrification has placed increasingly stringent demands for performance in electric motors. The most common type used in high-performance motors today, internal permanent magnet synchronous motors, or IPMSM, are now the motor of choice for electric vehicles. Our goal was to assess the actual current state of the art and see if we could deliver a 3 times improvement in key performance metrics for such motors using our novel two-phase cooling approach. The 4 basic metrics we were most interested in are specific power density, volumetric power density, specific torque density, and volumetric torque density. We thought that designers of electric vehicles would care about specific power density, but what we learned was that it's really, quote, launch that they care most about. This is the ability to rapidly accelerate off the line, the 0 to 60 mile per hour spec and the time in the quarter mile spec. Manufacturers like Tesla and Porsche are using these specs as key selling points in getting drivers to switch to EVs. Thus, high volumetric torque is what is desired since they do not want the motor package volume to intrude into the cabin space. We have estimated the market for high-end EV motors, the OEMs of which would care most about performance, by focusing on the luxury vehicle segment, and is typically defined as approximately 5% of all cars. At an estimated 27 million EVs by 2030, we estimated the number of high-end electric vehicles to be 5% of this. At 2 motors per vehicle, this would net to 2.7 million motors that might benefit from enhanced performance. We believe this is conservative since the EV pickup truck segment, such as Tesla's Cybertruck, Rivian, and Lordstown Motors, will also market high torque for pulling large loads and could add significantly to this market. We also engage with several stakeholders in the electric aviation market. Currently, state-of-the-art battery energy density limits electric aviation to 2 major application segments. 1, short-haul fixed-wing aircraft that fly between regional and municipal airports, and 2, multi-rotor aircraft that will be used primarily for urban air mobility or UAM markets, shuttling commuters from suburban, exurban, or rural areas to city centers to land on top of buildings for a short Uber ride for that last mile of the commute. Weight is everything in aircraft design. So while specific power density is clearly important, it is specific torque density that truly matters. This is because the ascent phase is most energy intensive for fixed-wing aircraft. During takeoff and climb, peak power can be 3 times that needed at cruise, when lift from the wings balances against gravity and thrust is used to push the aircraft forward. High torque is used to minimize the time in the takeoff and climb phases so as to minimize the total energy consumed in getting to the cruise phase. For multi-rotor aircraft, high torque will relate directly to thrust since there are no wings, so whatever improvements are made to specific power and specific torque, these will be magnified by the number of rotors for that particular vehicle. This nascent market is seen growing tremendously over the next 10 years. A recent Booz Allen Hamilton study projects, in their most conservative form, 55,000 daily trips in 4,100 vehicles in the U.S. and a market worth $2.5 billion, or, with its most optimistic set of assumptions, 11 million daily trips in 850,000 vehicles for a market worth $500 billion annually. Companies such as Lilium, Aviation, Joby, and EHang are looking towards explosive growth in the coming decade and will be searching for the most efficient motors.